Okay, so today we're talking about L'Hopital's rule. L'Hopital was a French guy from the 1700s, and he was actually pretty interesting. He was born into a wealthier family, was in the military at the beginning of his life, and then was drubbed out of the military for having poor eyesight, so he decided to get into what else but math. He made a connection with the Bernoulli brothers, who weren't very well off, but they were really good at math. And he basically made a career of paying them and others for their ideas and then publishing them in a few books. And he didn't really get a good rap for it, but he did make a lot of what could otherwise be math that people wouldn't normally read fairly accessible for the common person. So, interesting fellow, and they have named a fairly common rule in calculus after him, L'Hopital's rule. L'Hopital's rule only gets used when you're using limits, and specifically only with a limit that ends in an indeterminate form. Indeterminate forms are anything like 0 over 0, infinity over infinity, so on and so forth. We see the rest of the list here, nothing too bad. And they're called indeterminate because they don't actually tell us anything. And a lot of first year students make that big mistake of saying, oh, 0 over 0, that either means that it's 0 or that it doesn't exist. And that isn't necessarily true. It just means we can't determine what the limit is at that point. Sometimes you might have to look at the actual graph to determine the limit. Other times we can actually find it algebraically, a lot of times using L'Hopital's rule. So, simply stated, L'Hopital's rule says that if you have a limit, as x approaches a, of one function over another function, and when you plug that a into both functions, because remember, ideally with the limit, you want to be able to plug what it's approaching into the functions. If when you plug a into the functions, you get an indeterminate form, any of these up here, then we can use L'Hopital's rule. And L'Hopital's rule says that if when you plug a into the functions, it doesn't work, you get an indeterminate form, then instead we can actually take the derivative of each function. We don't use the quotient rule, nothing crazy, it's just the easiest derivative of your life. Take the derivative of the top, derivative of the bottom, and then try plugging a in again. And if a gives you an indeterminate form, take the derivative again and again and again until you actually get an answer. So a lot of times this has the nice quality of simplifying a function down to something that's a little bit easier to work with. Just be super careful because you're only allowed to use L'Hopital's rule if you have an indeterminate form. If it doesn't end in that 0 over 0 or infinity over infinity, if it's like, I don't know, say 6 over 0, you can't use L'Hopital. That's not indeterminate. So just be careful on it and we should be just fine. So, only 4 examples for today, and they go fairly quickly. The first one is one of those limits that most of your Calc 1 or AB calculus teachers tell you have to memorize. You have to memorize. However, L'Hopital's rule gives us a way to approach this without using the squeeze theorem or anything weird. So, the limit as x approaches 0 of sine of x over x. So let's say that right away you try to plug 0 in. So we say, okay, we can evaluate this. Sine of 0 over 0. Sine of 0 is 0. So we get 0 over 0 and go, drat. Indeterminate form, doesn't tell us anything, doesn't work. However, we did get that indeterminate form, so now we can apply L'Hopital's rule. We take the derivative of each piece. Derivative of sine of x is cosine of x. Derivative of x is 1. And now we can substitute in 0, and we find cosine of 0 over 1. We know cosine of 0 is 1, and 1 over 1 is 1. So we see one of those special limits that they've always told you you have to memorize is actually pretty easily found just applying L'Hopital's rule, basic trig value, and you're done. Second one. Sometimes you have to apply L'Hopital's rule more than once, and this is one of those cases. Here we're going to look at a limit as x approaches infinity. So again, maybe you try substitution right away, and you say, okay, we can substitute in infinity, though that's kind of abusing the math notation here, but either way we get the point. And you get e to an infinitely large number, which is in itself infinitely large, and then you get an infinitely large number squared, which is still infinitely large. They're two different quantities of infinitely large, but still it doesn't tell us anything. So we go, okay, didn't work, now we apply L'Hopital. So we can take the derivative of each piece, and nicely the derivative of e to the x is again e to the x. The derivative of x squared, 2x. We say, okay, now let's try evaluating at an infinitely large number. Infinitely large number over 2 times an infinitely large number, still an indeterminate form. Okay, well, let's try L'Hopital again. Trying again, we end up getting, as x approaches infinity, e to the x over 2. So now we have e to the x over some constant, which gives us an infinitely large number when we plug infinity in over 2. And we know something infinitely large divided by 2 is still infinitely large, so our limit is positive infinity. Or on the AP test, it's completely appropriate to put does not exist. They will accept either one. Okay. Now, our two most common, scrolling back up here, our two most common indeterminate forms that we deal with are these two. And I've never seen anything else besides those two on the AP test, but it's good practice to see if we can work with any of these other weird ones out here. So I'll give you one example, but the general idea is if you get an indeterminate form like one of these, start over with the limit and see if you can play around with the functions. Apply some of your algebra skills to rewrite the function so it's in this form of indeterminate form, either 0 over 0 or infinity over infinity. And if you can do that, then apply L'Hopital's rule. So we take a look here. Okay, and we end up with the limit as x approaches 0 just from the positive side of x times ln of x. And there are two reasons we're looking at this from the positive side. Reason number one is it's important to remember that if you can prove a two-sided limit, so assuming the positive wasn't there, then that automatically means that the one-sided limits are equal. Of course, we do have to be careful there because in this case there would be no limit as we approach 0 from the negative side, just because of that natural log function. Remember, we can't have any negative numbers, so as we approach 0 from the negative side, there is no function. However, the idea is the same in that we can try to go ahead and plug in 0, and if we get an answer, then we just realize, well, that's only the positive side because there's nothing on the negative side. So, let's try to plug in 0 right away. We go, okay, we end up with 0 in for x times natural log of 0 from the positive side. And that could be a little bit tricky if you can't visualize the graph. We basically have, well, let's look at natural log of x. Just a quick sketch of a graph. We remember that we go up and out something like this. We can never plug in actually 0. And as you get closer and closer, we approach negative infinity. So really, if we're looking down here as we approach 0 from the positive side, the y values approach negative infinity. So that tells us that we get a 0 times negative infinity case, which is another one of those indeterminate forms. So we go, okay, great, we can apply L'Hopital's rule. But applying L'Hopital's rule here, things get a little bit tricky. Okay, so imagine if we just tried to apply it right away. We'd say, okay, the limit as x approaches 0 from the positive side. Trying to apply L'Hopital, we end up with 1 times 1 over x. Then we plug in 0, and we get infinity again, which really doesn't help. That's not what we're looking for here. So instead, let's use that technique I suggested above and try to rewrite it in the form of either 0 over 0 or infinity over infinity. And the way we can do that is just by remembering that we can always move a power to the denominator, not a power, a function to the denominator just by changing its exponent. It's x to the first power here, so this should be the same limit as the natural log of x on top over x to the negative first. So remember, writing a negative exponent, we could pull this back up top and say, okay, now it's a positive x. And this is useful because plugging in 0 from the positive side, then we end up with an indeterminate form, infinity over infinity. And we go, all right, great. Now let's go ahead and apply L'Hopital. We can take the derivative of each piece, and we end up getting 1 over x over negative 1 x to the negative second. Okay. We can probably simplify this a bit. Maybe rewriting, we'll keep the top the same. The bottom we can say is negative 1 over x squared. And then realizing that these are two fractions divided by each other, we can rewrite and say this becomes 1 over x times x squared over negative 1, which really simplifies down. Let's maybe take over down here. as to the limit as x goes to 0 from the positive side of negative x. This is much easier. Plug 0 in here from the positive side, and as you get closer and closer to 0 for just the function negative x, you get closer and closer to 0, and we're done. Again, this type of problem is not super common. I haven't seen it on the AP test. You'll probably see it in your book, though. Don't spend a ton of time on it. This last type of problem has become more and more popular over the last 5 or 6 years on the AP test, and there are numerous different ways to do it, but I like the fact that you can apply L'Hopital's rule here, and let's see why. In this case, we're dealing with a limit that actually has an integral function inside, and note the dummy variable there too, right? It's one of those things where if you see t's here and you see x's up here, it's probably going to be the case where you'll have to take the derivative, and it's going to be a good application of the second fundamental theorem of calculus. You'll notice x is everywhere else here, and probably what you'll have to do is take the derivative with respect to x, and then you'll end up plugging x's in for t's so that we only have x's everywhere throughout the problem. But let's see why this is an application of L'Hopital. Whenever you first have a limit, always try to plug that limit in. So we're plugging 1 in for all the x's. So we still have those t squareds dt over 1 squared minus 1. Okay, and we go, all right, well, what did we do at the top? We know any integral from some number to itself is always 0, because an integral is just a measure of the area under the curve, and if you go from one number to itself, there is no area. Over the bottom, 1 minus 1, 0 over 0, indeterminate form. Cool. We get to use L'Hopital's rule. Let's see what happens. With L'Hopital, we do want to take the derivative with respect to whatever variable is approaching a. So in this case, we'll take the derivative with respect to x of the top and bottom. So it'll look something like this. The limit as x approaches 1, d dx of this monstrosity, 1 to x, e to the t squared dt, over d dx of x squared minus 1. And you don't need to write the d dx part, but I think it gives you a good visual of what's going on with that second fundamental theorem of calculus. So limit as x approaches 1. Remember that second fundamental theorem says we take whatever's up here, we plug it in for whatever our variable is, and then we do have to multiply by the derivative of what we're plugging into, so the derivative of x. So it ends up looking like this. We end up with e to the x squared times the derivative of x, which is just 1. And it's always important to remind students to multiply by that derivative, because even though it's not as common in AB, it does show up, and BC it definitely shows up. So you need to really hammer in the idea of plugging in and then multiplying by its derivative. Over derivative of x squared minus 1 is just 2x. Alright, now let's see if we can evaluate at 1. We end up with e to the 1 squared times 1 over 2 times 1. And I don't think we're going to get any indeterminate forms here. We just end up with e to the first over 2, which is really just e over 2, and we're done. So really have your students focus on a problem similar to this one and similar to the first problem that we saw as well. Those are the two that really seem to show up the most. Whether it's a basic problem, one of the first couple right on the BC exam, you have to take the derivative of each and plug in, or it's one of those that actually has an integral in the problem and you have to apply the second fundamental theorem of calculus. Okay. Hopefully this was useful for you, and as always, email me with any questions. Thanks.